Happy to have again Jaikumar for his final lecture on classical and quantum information theory.
So, thanks, Sumit. Thank you all for coming back. So let's quickly review what we did last time. We've been discussing these entropic quantities, the entropy of X, the conditional entropy, mutual information. And so far, we've related them to the growth of typical sets. Okay, so if you sample things according to the relevant distribution, then typical sequences show up. Most of the probability resides on typical sequences. And the number of typical sequences somehow is controlled by such quantities. And this particular quantity, the mutual information between X and Y, for which there was a formula, showed up in our proof of Shannon's theorem about the capacity of channels. So now, what I'd like to do is once more draw a picture so that we have everything in one place. So suppose you have two random variables X and Y with some joint distribution, but we look only at X. Okay? And we draw samples according to X, and we get the alphabet of X is A. X spits out values in A, and we do this K times, and we get a typical set, and the size of this was, as we increased K, it grew exponentially. The coefficient of K was h of X. Okay. And on this side, there was Y, which took values in a set B according to its own marginal distribution. And as we picked things or sampled Y again and again, Y alone has its own typical set and its size. There's nothing new. I'm just substituting. Instead of X, I'm writing Y. Okay, so this we probably saw in the very first time we discussed these things. Now, if you look at any particular typical sequence on this side, and you connect two sequences, if they together, an X bar here and a Y bar here, are jointly typical, then we draw this edge. Then, our understanding from last time is that the number of edges going out of a single X bar grows as 2 to the power K H . And so it's roughly uniform. All typical sequences have the same number of edges or lines going out of them. And on this side, this number looks like 2 to the K times H of X. So that is how we understand these quantities. So when you sample things from a joint distribution over and over again, you get typical sequences. Any one typical sequence here is connected to a certain number, and so on. Okay. So if we ignore the rest, because they rarely happen, we are basically left with what is called a bipartite graph, where the number of vertices on the left is this, the number of vertices or nodes on the right is this, and the number of edges is this times this, or this times this, and these two numbers have to be the same because they're counting the number of edges. Okay. But let us ask, what is this quantity? Yeah. In this language, what is mutual information in this language? What is the total maximum number of edges possible between this part and this part? If this has a certain size, so if this has, say, T vertices, this has S vertices, if we had connected everybody with everybody, we would have got T times S edges. Yes? Okay. So so let me write this down. 2 times K H of X times 2 times K H of Y. This is the maximum number of edges possible. Yeah. And how many edges do we actually see in this picture? There are these many vertices. Yes? So this is roughly the density of edges in this graph. You understand? The total possible is this, total present is this. What's the density? Yeah. And if you look at this number, what does it look like? Would you like to? So mutual information also lives in this picture. It lives as the density of edges in this picture. Is this okay so far? Yeah. So everything that we have talked about is just this picture. So where does question? Symmetric. In fact, I mean, if I had not done this and I had been more honest about it, I would have said, how many jointly typical sequences are there at all? I mean, that has a law. That should grow as, the number of edges should grow as 2 to the k times xy is a variable on its own. It has its own entropy. So that should have looked like, so this, instead of writing this as the numerator, I could have written this as the numerator. And then you would have seen that it is 2 to the power minus k h of x plus h of y minus h of xy, which would have been the symmetric formula for mutual information. But I agree. Yes, all this explains why, after all, mutual information is symmetric. Okay. All right, I just wanted to make one more comment about Shannon's theorem. So what does Shannon's theorem say? This density of edges, we would like to keep them small because when I do, so in Shannon's theorem, the left side is what we push into the channel. The right side is what comes out. And we would not like things corresponding to different code words to clash. Yeah? That is, when this is sent into the channel, it sprays its probability over these many choices, roughly uniformly. Okay? And if this graph were sparse, if its density were small, then we would see that things that go out of this are unlikely to clash with things going out of this. So that's why in Shannon's theorem, we try to maximize this so that the density of edges here is small. But we maximize this by doing what? The channel characteristics, the conditional distribution of y given x is already given. That is the channel. That is what we are given. What can we change in this graph? The only thing we get to change in this graph is the distribution of x, because then that induces a distribution on y according to the conditional distribution. Okay? So as we change the distribution of X, what changes? This set grows or shrinks. Yeah, because as we change our X, the entropy changes for X. So this set increases. This degree also changes. And there is a sweet spot where, so as this increases, the denominator increases. You understand? Yeah. Sorry, so this is, so as, whichever way, so as we increase this, this also can change. Yeah. But we optimize this X so that this quantity is maximum, so that this edge density here is as small as possible in absolute terms, okay? And we do the transmission at that sweet spot, okay? That is, we design our code words according to that empirical distribution. Was there a question? Yeah.
Your h of y given x does not depend on h of x and h of y, right?
H of y given x depends on on x. I mean, yeah. So let's write down the formula. Yes, so I understand. There is a y given x, and one says that the channel completely determines the conditional distribution of y given x. So one starts believing that maybe h of y given x doesn't depend on x at all. That's not true. What is this is h of y given x. These objects don't depend on the distribution of x. X has been set to A, but the way they are being combined to compute the average. These PAs are probability that x takes the value A. Yeah. So which averaging you are going to do here, what weights you are going to assign to these quantities depends on x. Is that okay? Or sorry, so if there's something puzzling about this, this is the time to ask.
Channel, what the channel is doing has not to depend on what your input is, right?
That channels, okay, so yeah, it all depends on what you mean by that. The channel tells you, channel consists of all these numbers. Yeah. Okay. Channel's behavior doesn't change based on what you intend to do to it. I mean, you say, I'm going to feed things according to this distribution, because that doesn't, I mean, it doesn't read your mind. But definitely what it outputs depends on what you input. If you send it A, then the B's will appear according to some distribution. If you send it A prime, B's will appear according to a different distribution. Yeah. So I agree that the conditional distributions don't depend on the frequencies with which various A's are arriving at the channel. But the entropy of the quantity that we are computing, yeah, the entropy of y given x, that has the distribution of x in it. Okay, so we cannot just say that the conditional entropy depends only on the conditional distribution. So this is what I wanted to say. So what Shannon's theorem basically tells you is that if this is the picture and we want to transmit at the best rate possible, we should somehow choose the right distribution here, yeah, for x, so that this graph is as sparse as possible, so that clashes occur only rarely. So that's all I wanted to say about what we did last time. So it's possible to study these quantities for themselves, and there's a large part of information theory and many applications that arise out of studying these objects by themselves. Now, this series of 3 lectures was, it's clear to me now, was like advertised falsely as classical and quantum information theory. So, I mean, that was my intention. I don't know if you believe me. But what I'm going to do today is show you some applications of these quantities. And there's one thing we haven't talked about, that is relative entropy. So I'll tell you about that. And in the course of these, one or at least 1 or 2 applications of inequalities that arise here will involve von Neumann entropy. So that will be my tiny tribute to this, the topic of this program. Okay, yeah. So let us write down our entropic quantities again. So h of x is, writing it in a different way, yes, yeah, just understand. X and Y have some joint distribution. This expectation is over all possible choices of X and Y. And we write P, B given A. When, yeah. And if you, a special case of this distribution, this definition you might say is this quantity. Yeah, so in information theory, sometimes we write X, Y without the commas. You shouldn't read it as multiplication of X and Y. Yeah. And this is expectation of log of 1 over P of X plus the expectation of log of 1 over P of Y given X, and which is h of x plus h of y given x. So, yeah, we didn't really need to count edges, etc. to see this. It is directly sitting in the formula itself. Okay, that's all I wanted to say. Sorry? Oh my God. I'm very sorry. Yeah, I copied that. Yes. Thank you. Yeah. So if we look at this or either of them and try to write h of x colon y in this same language. So do you see this? It looks like log of p So if I write h of x plus h of y minus h of xy, so this is the relative entropy of 2 distributions. The current joint distribution, yeah, and so this is the product distribution. So look at x and y, they each have their own distributions, and this is as if the samples are being drawn according to the product distribution, they are independent. And this is according to the distribution that we have currently. And what the mutual information measures is how different your current distribution is from being truly independent. And we saw that Gibbs inequality, that this is a special case of relative entropy. And relative entropy is always greater than or equal to 0. I mean, if you look at relative entropy of two distributions, it looks like now P and Q are two arbitrary distributions. Sometimes P may be greater than Q, and sometimes Q may be greater than P. That all these quantities are non-negative is obvious because all these numbers are greater than or equal to 0. When we look at relative entropy itself, there are negatives and positives here. Yeah, but somehow Gibbs assures us that the expectation will always be greater than or equal to 0. Okay, but of course, I mean, information arises in Shannon's theorem and it makes no sense for it to have been negative there. But I'm saying that this inequality can also be verified. So one of the consequences of this is that mutual information is always greater than or equal to 0. Right? And what is mutual information? This is always greater than or equal to 0. I'm just rewriting this inequality, which means conditioning only reduces entropy. If you take, this is the entropy of Y, this is the entropy of Y given X. And this difference is called mutual information, which we know is always non-negative, which means conditioning always cannot increase entropy, only reduces entropy. I mean, from an information theory, I mean, if you just believe that there is something called information, then it's kind of obvious that the amount of information that we know from Y would be less if we already knew X. Yeah. Learning about Y cannot give us more information just because we have X. Okay, so this needs to be read rightly. Yeah, but that is good. Now,
Question,
yes.
Yeah. So is there a difference between mutual information and relative entropy?
Yes.
Here, what does it correspond to?
So mutual information is the relative entropy of two special distributions. The product distribution and the true distribution. So maybe I should explain. So we've been given a distribution, a joint distribution for X and Y. What does it mean? These are the various choices for A, F for X. These are the various choices for A1, A2, AN, B1, BM. To know the joint distribution of X and Y means we know the numbers here and all these numbers add up to 1. Is that, yeah, so that's, yeah. Now, instead, if I sum the rows, I would get a distribution here, and that's what we call the marginal distribution of X. And if I sum the columns, I would get the marginal distribution for Y. But then I could create a new matrix here, where in the A, Bth entry, I write PA times QB. And you can again check that the numbers all add up to 1. And this is another distribution, this is the product distribution. Okay. So this is one distribution, this is another distribution. How different are they? Okay. If X and Y were independent to start with, then these two matrices would be identical. And mutual information measures how different these are. Okay. So for example, suppose both of them had n choices and everything else is 0. That means X and Y are taking identical values. Whenever X takes the value A1, y takes the value, A1, y takes the value B1. On the other hand, if it was product distribution here, each of these entries would be 1 over n squared. Yeah. And in this case, if you look at the entropy between x and y, I mean, intuitively we believe that it should be the entire mutual information between x and y. It should essentially be the entire entropy of x itself, and it will come out to be h of x, because h of x given y is 0. Once you know y, you know x.
Sir, hello.
Is that okay?
Sir,
mutual information is relative entropy for some special distributions. But relative entropy can be computed for any pair of distributions on the same set, underlying set. Yeah. Is that okay? Sorry, what is relative entropy? Relative entropy between P and Q, I don't know, I thought I wrote it, is this. I will have something to say at the end about how we should read, what is the meaning of this. I mean, sort of said what is the meaning of h of x, what is the meaning of h of y given x, etc. in that picture. There is a good meaning for relative entropy. Actually, of all the entropic quantities, as time goes by, this turns out like to be the most important quantity, the relative entropy between two distributions.
Sir, I have a question actually. I'm talking online. Hello?
Yes. But clearly P and Q are not in an equal footing in the formula. That's right, that's right. So it is not symmetric. So is P the empirical probability distribution and something else that you're just comparing it with? Okay, so it will turn out that, yeah, so I was saying that I will tell you what relative entropy controls. Okay, so I'll say it a little later, but what it controls is, suppose you are drawing samples according to the distribution Q. That is, Q is the true distribution. But when you look at the samples, they start looking like they are from P. Okay, so what is the probability that when your true distribution is Q, the empirical distribution, I think the empirical distribution looks like P. Yeah, so I think you said it the other way. Yeah, so Q is the true distribution. What is the probability that the empirical distribution looks like P? Now we believe that if we take a big sample, then the true distribution will get closer and closer to the empirical distribution. That we will not be fooled into thinking that the distribution is something else when samples are being drawn according to Q. Okay, but the probability goes exponentially down as we draw more and more samples. But when things go exponentially down, by now we don't just remain satisfied by saying it goes exponentially down. We ask what is the coefficient in front of k in the exponent. And that coefficient will turn out to be relative entropy. Question? Yes? No, so yeah, so no, so relative entropy, we only define relative entropy when P should be 0. Whenever QA is 0 implies, sorry. Yes? Very large, yes. No. When we say this is the distribution of one sample, what we are talking about is taking k of them. Even if there was a slight difference, so let me draw this. So this is the distribution for, let's say, Q, and there was a place where Q was very small. and you said P there is perhaps very large. Yeah. So, and yeah, depends on this, because that is also here. P, yes. Yes. No, if we draw K samples, yeah, this particular letter A will appear very rarely when you sample from Q, and will be all over the place when you draw from P. Yeah. No, it is asymmetric in the sense that when you draw according to Q, what is the chance that the device is masquerading as P? Yeah. So I will write down a theorem towards the end, which will have this exactly there, and then we can look at it. Yeah. Okay. So I have said many things. And question, yeah, please. That's right. Yeah, I mean. Oh, I'm sorry. Is this what? Thank you very much. I mean, yeah. So yes, as the relative entropy increases, the probability of P masquerading as Q goes. Okay, thank you. Sorry. Yeah. Okay. So, by the way, so suppose X is a distribution on n things with its probabilities P1 to Pn. Yeah. So, if you compute the relative entropy of the distribution of P with the uniform distribution, yeah. And we know that every relative entropy is greater than or equal to 0. And if you look at this, you conclude that h of x is always greater than or equal to 0. And it is equal to log n when x is uniform distribution on those n things. Yeah, which you can get directly from the formula. Okay. So I want to show you an application of what we have written so far. So this is an inequality in combinatorics, but yeah. So this is why I don't know. Yeah, I'm always very scared of violating the right-hand rule when physicists are around. Yeah, so okay. So okay, so there are these n points here. Let's say capital N points in three-dimensional real space. Okay. And I project them down, and I see some number of shadows of those points, and that I call nz. Okay. Now, why would nz not be the same as n? Two fall on the same side. Okay, good. And there are ny here, and I project them along the x-axis, and there is nx. And the Loomis-Whitney inequality says that nx times ny times nz is always at least n squared. Yeah? Yeah, so let's look at a few examples. But if you had a cube, I mean, the corners of a cube, axis aligned, you would have a total of 8 points. Each projection has 4. 4 times 4 times 4 is 64. 8 square is 64. And somehow this is the worst that can happen. Yes, yes, yeah. So if you took it in d dimensions, projected it onto d minus, okay, let me do the proof and then you will do vast generalizations of this, okay? Yeah, but how do we prove this? Yeah, so let me start you off. Let me say a few English things and then we'll try to formalize it in the language of information. So my point is that although it looks like some inequality about numbers, it's actually an inequality about information. Why? Suppose I pick a point uniformly at random from these, yeah? Pick what is the entropy of x, y, z? If I pick something uniformly at random from n possibilities, what is its entropy? This is log of n. When I pick a point uniformly at random and I project it, if this original point had coordinates x, y, z, this point would have coordinates x, y. And I could compute its entropy. Now, all these shadows may not have the same weight. Some of them have more points above them, some of them have fewer. It is some distribution, but it's a distribution on how a set of what size? Nz. So this quantity is so let's just stare at this. The entropy of this is n, log n. These things have these entropies. But notice that every piece of information here is available from 2 sources. Yes, x, both these points are talking about x. Both these are talking about y, both these. So it must be, morally, that the information contained in x, y, z is being supplied 2 times over by these people. So this sum must be at least 2 times this, which is the Loomis-Whitney inequality. Okay. So if information was a thing, yeah, then we don't do any calculation. We just write the definition and we get it. Okay, so how do we formalize this? Yeah, I've just expanded this according to conditional entropy. Okay, and what is h of x, y? maybe you already see what's going on. Am I okay? Yeah. Now, I know the bounds on these. These are bounded by their respective logs. If I add these, do I get 2 times this? I mean, that was what my intuition told me, that the amount of information here is 2 times the amount of information here, because every variable appears twice. But if you look at it, h of x is being contributed twice. H of y given x, it is h of y given x, and this is h of y. And what do we know about the relationship between h of y and h of y given x? Conditioning only reduces entropy. So what is being contributed here is at least this. And each of these for the same reason, because this is h of z given x, it is conditioned only with x. This is conditioned even with more, x and y. So this dominates this. Each of these dominates this. So if you add these up, it dominates the right-hand side of this by a factor 2. But here, this is an equality. So if you add this up, it dominates this by a factor 2. And that is what our English used to say before, and now the math says the same thing. Is it clear? Yeah. So now, generalizations. If you are in d dimensions and you project them onto various coordinate subspaces, those subspaces don't even have to be d minus 1 dimensional. Yeah? So it could be a projection into the first 4 dimensions, sometimes 7 dimensions, etc. But if every coordinate appears L times among the projections, then you get to write an L here. Because each piece of information is available to you from L sources, that is what governs this inequality. I don't know. You like it? Yeah. No, it was based on the other big, using the Cauchy-Schwarz inequality. Yeah, and of course, they did it for volumes, but you can imagine that, volume, you can break it up into pieces and you can just take limits and get to volume inequalities.
You can imagine that this is like a continuous distribution.
That's right. Yeah. So that's right. So you could think of this as a body in 3 dimensions and look at the actual area of the shadow it casts on the 3 planes. Now, okay, I know. So, yeah. Then if you take the product of the areas, it will be at least the square of the volume. Yeah. And this is how I passed most of my school physics exams. The units work out, right? Yeah. So centimeter square, centimeter square, centimeter squared, and centimeter cubed squared is centimeter to the 6. Yeah, must be true. Yeah. Question?
So if there are only 2 directions, it kind of looks like the uncertainty relationship, but like, is it any related?
Yeah, I don't know. Yeah. So.
But there is still a version for 2 dimensions?
Sorry, for?
Is there a version for just 2 dimensions?
2 dimensions, it's kind of very easy. If I take a body and I project and I get this as the span and this as the span, I know that the body is confined to this box and the area of the box is this times this. So in 2 dimensions, yeah, it's not so remarkable. But in higher dimensions, it's not clear. One starts worrying if the body is skewed or shaped. We don't imagine, the body doesn't have to be convex, doesn't have to be anything, but still the inequality holds. But then what? Yeah, so suppose it was very dense here and sparse here, but what do we mean by n of x? And then what do we do with this? Yeah, if you say compute the entropy of this, then we are back to the same thing. Yeah, but if we otherwise, here I'm just talking about the span, whether it is thinly supported or heavily supported, I don't care. I'm just calling it an area. But you're right, the actual inequality is h of x, y, z, commas in between, is h of xy plus h of yz plus h of xz. This is the master inequality, okay? And then it turns out that they are related to this. We set up the distribution so that this becomes equal to log n, and these distributions, these entropies are bounded above by log. Question? No, I mean, this is just information. So if you can reconstruct the point from your projections, so you can do a linear transformation on this space and everything will still hold.
Like if you consider coordinate transformation.
Yeah.
Are these x, y,
Yeah, their orthogonality was never a question. I mean, we never used that fact. Yeah, a point is described by 3 parameters, x, y, and z. The parameter x, y is available somewhere. So that's all. Yeah. Yes, please, please.
are you going to talk about the quantum generalization?
No.
Then can I ask a question?
Yeah.
So like if I naively consider quantum generalization, I naively expect if the x and y and z as a measurement operator, but then there is some case where x and y are not commutative. So like
We can't even talk about them simultaneously. Yeah. Yeah.
So is there any this kind of quantum generalization which involves non-commutative operators?
Yeah. So all this comes under, I mean, there's a generalization which looks like this, called now, I'm not able to recall whether there is something called quantum Scherer's lemma. Okay, so I don't know the answer, but a short internet search saying quantum Scherer's lemma would tell you everything that is known about it. Okay, so yeah, I just want to show you one more application. I mean, suppose, yeah. and you can define its von Neumann entropy. Sorry, I don't know which log you use, but let me just use log base 2. Yeah, okay. So what does this actually mean? I mean, it's the same. So if you write down, say, rho in its eigenbasis, let's say lambda 1, lambda 2, lambda capital N, yes, these are zeros. Then these lambdas can be regarded as probabilities, and you compute the Shannon entropy of these probabilities. That is what is von Neumann entropy of this. Yeah. This is entropy of however, we could, of course, write this rho in any basis and, yeah, and look at so you take your original rho, not necessarily in its eigenvector basis, and you erase everything away from the diagonal, you retain only the diagonal. So this is also a probability distribution, and it has its own entropy. Yeah. Point is that, yeah, so what I have done is a very basis, and the inequality I'm going to write is, yeah, so the Shannon entropy, so I mean, you know all this, but the von Neumann entropy is the Shannon entropy, is the minimum Shannon entropy that you can get by this procedure, by changing basis. Once again, let me say that again. So you took this rho, yeah, it is a density matrix. You could write it in various bases. And depending on your basis, you will see something on the diagonal, you erase everything. It's as if you performed an orthogonal measurement on it and you got various probabilities. Yeah. That distribution has its own entropy because now it's a classical distribution. And yeah, so let me call this P. And for every way, yeah.
Sir, is there any restriction on the kind of basis transformation you can perform?
I mean, I meant unitary, of course. Is that?
Okay, sir.
Yeah, yeah. I mean, you do basis transform according to, I mean, whatever you do in quantum mechanics.
So if you had a basis transformation to go to a diagonal matrix, then this would be equal.
No, no, I'm not saying you wrote this, you did a basis transform and forcibly erased everything. The diagonals would still be probabilities. They sum to 1 and they are non-negative. Yeah. And that probability, you could now treat this, I mean, it's sitting on the diagonal, but you could treat this as a probability vector. And this was a probability vector also sitting on the diagonal and compare their entropies. The minimum you would achieve is called the von Neumann entropy. You could say that it's a perverse way of defining von Neumann entropy. Take the density matrix and do that measurement, which would give you the lowest entropy, and that is called von Neumann entropy. So I just need to, I mean, if we want to think of that as the von Neumann entropy of a density matrix. You're given a density matrix. If you were to observe it, depending on the basis, orthogonal basis that you choose, you would get different probabilities. Choose the one so that the entropy is minimum. For example, if this was a rank 1 density matrix, I mean, if you did it in some crazy basis, you would probably get numbers all over the place and it would have entropy. But if you chose its special basis, you would get this as 1 and all the others 0, and entropy will collapse to 0. And von Neumann entropy of a density matrix is the minimum that you can ever achieve. Oh, that is what you do when you do measurement. Okay, at least that's the way I... You just apply a complete system of orthogonal projections onto one-dimensional spaces. Yeah, I mean, yeah, when I observe a qubit in a certain basis, I get a probability, and after that, if I say, I performed the measurement, but I haven't looked at it, what is the state? It is a probabilistic state, which is in 0 with this probability and 1 with this probability. Sorry, I probably have a problem of language at this stage, but I hope it's okay. Yeah. Sorry?
Think of rho of D as an expectation.
Yes, yeah, but you would probably multiply it with some operator and take trace to get the expectation. The entropy is actually increasing. So yeah, I mean, yeah, I don't know, somebody else should answer this question, but I'll just prove this inequality. Sorry? I don't know, yeah. But yeah, I mean, when you're given a density matrix, what should you consider is entropy? Well, one might say it depends on the basis, but you say, what is the lowest that you can get out of it? Okay, and that is called von Neumann entropy. I mean, I'm defining it that way. And that it's reasonable because of that inequality. Yeah, question?
Can it be related to data processing inequality?
So there is a data processing inequality, but so I'm not able to immediately see the connection. It is just convexity, yeah? It is convexity and...
but this is a channel. I mean, that arrow is a channel.
That's a channel, yes. Yeah. This arrow is a channel, yeah.
So just one clarification I needed. So you are taking rho and you are performing some kind of basis transformation on that rho, and you are just removing all the non-diagonal entries and just considering the diagonal entries to get rho d.
Correct. Is that okay? Sorry.
Yes, sir.
I'm sorry, I'm probably saying obvious things in strange ways, and that's why everybody is puzzled, but so let me draw these numbers P1, P2 to Pn, and the entropy was computed, von Neumann entropy was computed with respect to lambda 1 to lambda n. And clearly, whenever you do a basis transformation, these Pi's are some linear functions of these lambda i's. Yes, if you multiply this matrix on the left and right by a unitary transform and unitary matrix and its conjugate, what you will get is that each diagonal entry here is some linear combination of this. Okay, yeah, and this is not the way one says it, but I would like to tell you this. Yeah. So it is some matrix times these numbers. And it turns out, if you think about it, here there will be various entries, mij's, yeah, m11, m12. These numbers, this is actually a doubly stochastic matrix. Which means if you look at all these numbers are non-negative, and if you look at the row sum and the column sum, they all add up to 1. Okay, you will check this, yeah. So how are the diagonal entries of the matrix after after the change of basis dependent on the original eigenvalues? Take the original eigenvalues. There are some numbers that arise based on the basis you use, but whatever numbers that arise always have this pattern that they are a doubly stochastic matrix. Okay, times this. Yeah. If you've seen this, it's totally obvious. If you've not seen this, you have to do a small calculation. No, it is, if you look at the basis vectors, they are, if the original basis vectors were the W.
Yeah. So that's the unitary transformation, and it's the absolute square.
That's right. Yeah. Because when people used to do classical randomized computation, from one state, you evolve to another state. And how do you evolve? Well, or a channel. If you are at a certain state, next step, you move to another state with various probabilities. So the columns, whenever columns look like probability vectors, they are called stochastic matrices. Okay? Like a Markov chain. Yeah, like a Markov chain. Yeah. Okay, so anyway, so thank you. So it is precisely these numbers, and you can see that because all our vectors are unit vectors, the row sums and column sums all are 1. Okay. Now, every doubly stochastic matrix whenever you have a doubly stochastic matrix, it is a convex combination of permutation matrices. What do I mean by a permutation matrix? Permutation matrix is a special kind of doubly stochastic matrix which has 1, 1 in each row and each column. Yeah, so it corresponds to, so if you take a vector and hit it with this matrix, it will just permute the entries of it. Is that clear? So if you take, say, lambda 1 to lambda n, and multiply it with this, you would get lambda 1 to lambda n, but in different positions. And what happens to the entropy when you hit it with a permutation matrix? If you take a probability vector, hit it with a permutation matrix, what happens to the entropy? Stays the same. Okay. So this is, so imagine that this is the distribution. Yeah. So x is a random variable which has the distributions given by lambda j. And this is a convex combination of permutation matrices. That means M can be written as summation q sigma, where sigma ranges over some set of permutations. And these q sigmas are probabilities. Yes? Okay. No, the same M can be written in multiple ways. Pick one realization, write it down. Okay. So then, if you, think of the vector. It is this summation over sigma, q sigma, m sigma multiplied by So now, so x was this random variable, and let sigma be picked according to this distribution. I'm just writing it crudely as this, yeah. And consider the random variable sigma of x, yeah. So you take the random variable x takes values 1 to n with these probabilities. Sigma of x, well, it just jumbles up the lambdas. It takes 1 with the probability lambda 5, 7 with the probability lambda 12, and so on, but it is just permutes the values 1 to n. Now, what will be the entropy of or let me just write h of sigma x. So as I average over the sigmas and think of this is the same distribution as P. Yeah. So this is the entropy of P. And so what is entropy of sigma x given sigma? Once I tell you sigma, then sigma x is just a version of x with values in different places. So this has the same entropy as h of x. And this, we already know that conditioning only reduces entropy. Okay? So h of p, was the entropy here, which was h of that, I don't know, what did I call this? This was called PD. And h of x was, in fact, Suvrat. Okay. So, as somebody said, this is just convexity. The fact that conditioning only reduces entropy is also convexity. It's just convexity said in the language of information theory. So, yeah. So now, so these were the two sort of applications of the familiar information theoretic inequalities that we saw. So in the remaining 15 minutes or so, I would like to get back to relative entropy and tell you the theorem that I had mentioned initially. Questions? Yeah, one last time. A to the power k is the set of all possibilities that can arise when I sample according to the distribution Q. Yes? Okay. So there are many, many strings here. And here, each string, little x bar, has its own probability that is given by, if you look at a string x bar, it has its probability. It was being drawn independently. Yeah. So now there is this set F here. And inside of F, if you look at the letters, so here there are strings, let's say y bar here. So you sample a string from F according to the conditional distribution. But inside of F, if you look at letters A, they don't quite show up according to the distribution Q, but they're different from Q. They come up according to distribution P. So it's as if there was a source which was emitting symbols according to the distribution Q. And you were there collecting K of those symbols, and whenever you liked it, you let it pass, otherwise you killed it. Okay? And you let a certain number of certain kinds of sequences pass. And those sequences that you let go through are this collection F. But you were very careful. You were trying to fool the person on the other end that your empirical distribution is P rather than Q. So the source was emitting it with distribution Q, but you were filtering it and sending only things so that they had a slightly different empirical distribution. Okay. At what rate will you be able to send strings over? Okay. If the true distribution is Q, and the distribution you are trying to sort of fake is P, then if the distribution you wanted is also Q, then you can let every string pass. The person on the other end will see the same empirical distribution. But if your distribution that you want is substantially different from the distribution Q, then your probability, this set, will have very small probability. Yeah? That is what it says. That if the distribution inside of F, this is just a funny way of writing sampling conditionally from F. The probability of the string, so this is X belonging to F. Probability of the string divided by the probability of the whole set. And then you're picking one particular symbol from this string and giving it out. But, I can explain this if you want. But this is what is emerging out of your filtering. Okay? If you would like to take an original source which had a distribution Q and construct out of it a source, which has distribution P, the rate at which you can use the samples of Q, that is, you will be able to use only this small fraction of the samples that are coming out of Q, the strings that are coming out of Q, most of them. So if this number is like 1/10, then you'll only be able to let 1 in 10 sequences pass. And the farther away you want to make P from Q, the worse your rate of extraction of randomness from Q will become. Okay. And what governs this probability is the relative entropy between P and Q. If P is very different from Q, So for example, you could say that, look, I have sequences that are, produce, or my original source was generating head and tail with equal probability. But then I only restrict myself to those, or I want to give the impression on the outside that this coin, which I was tossing, is actually a biased coin. So as sequences go, I suppress them. And only those sequences which have, by chance, a large number of ones, I let them pass. And if I want to create the impression that there are 3/4 ones and 1/4 zeros, then my probability of success, if I try to do it for k samples, will go exponentially small, and this number governs my rate of success. Okay, so I mean, this reminds me, maybe, this is all I wanted to say. The proof is in the notes, but you should try and prove it yourself. Maybe I'll say one more thing, but before that, a story. I don't, many of you might have heard, there's a story about Onkar and the baker. How many of you know this? No? No, you've seen this? So, so apparently, I mean, I don't know if this is true, but Onkar used to go to a baker, and I don't know what units were used in France in those days, but let's say it was, the bread was supposed to weigh 1 kilogram, and he found that it was less than 1 kilogram, let's say 900 grams. And he reported the baker to the authorities. I don't know if they fined him or something. And then onwards, whenever Onkar went to the baker, he always found that his bread weighed at least 1 kilogram. Okay. But Onkar was suspicious. He wasn't sure the baker actually had changed his dye or whatever you used to mold the bread. So he plotted the weights, and he actually concluded that what the baker was doing, he hadn't changed anything. Baker himself would weigh the bread. One or two of them would always be more than 1 kilogram, and he would keep them aside. And when Poincaré showed up, he would give it to them. Yeah. So even though the underlying distribution was Q, he was trying to fake, trying to create the distribution P, at least its mean, to be above 1 kilogram by sampling from this. The question is, how many breads did the baker have to bake before he would find one which would pass the Poincaré test, yeah, the filter. Yeah. And that rate, I mean, if you make the same story here, is like this, that yeah, the farther away your distribution is from the true distribution, the longer you will have to wait in order to produce such a thing. Good. So let me stop now. You've been very patient. If there are any questions, I'll answer. I know I didn't say anything significantly quantum in all this, but there's the whole program for it.
Questions?